So as the activity we just did shows, simulation is definitely a powerful method for modeling chance behavior. And so in this section, section 5.1, we're going to begin by examining the idea of probability and then illustrate how simulations can be useful to estimate probabilities. Then we're going to move on in sections 5.2 and 5.3. We're going to develop the basic rules of probability, and we're going to introduce some helpful tools for displaying possible outcomes from a chance process. So we're going to look at two-way tables, Venn diagrams, and tree diagrams. And as you all know, probability calculations are the basis for inference. And so probability is the branch of mathematics that describes the pattern of chance outcomes. So what would happen if we did this blank amount of times is basically the question we're going to be answering. And so it's the reasoning of statistical inference rests on asking, how often would this method give a correct answer if I use it many times? So an everyday example, most of you drive to school and you drive or pass through the intersection of the red light. It seems the light is never green when you get there, and you know this can't be true. In fact, if you think about it, you can recall sailing through the green light at least once in a while. So what's random here? The actual light is governed by a timer, and the time you arrive at the light is random. So even if you try to leave your house exactly at the same time every day, whether the light is red or green when you reach the intersection is actually a random phenomenon. So that's one case. Another is that chance behavior in the short run is unpredictable, but it has a regular and predictable pattern in the long run. And so that's how many times you're actually going to do a simulation. We call that repetition. So what we're going to do now is you're actually going to do an activity on your own. It's a probability applet. So this is the website you need to go to. I do have a link for mine, so I'm going to go there directly. And this is where you should end up. It's the probability applet. So we want to know, what we know is that the probability of heads or tails when you flip a coin is 50%. Half the time you're going to get heads and half the time you're going to get tails. But what we're going to look at in this applet is what happens after you do more and more repetitions. So we're going to start out by doing 10 tosses. I'm going to go ahead and reset this. I'm going to toss the coins. Over 10 was random because there are times and just kind of do point. You're expecting this get statistical app time. Okay, hopefully you had a chance to do the simulation, and what you should have noticed is that random is not necessarily haphazard. They don't mean the same thing. It's actually, random is kind of a description of an order that emerges in the long run. And so though it was random to get either heads or tails, in the long run it is going to approximate the true probability, which is 0.5 in this situation. And so this was a simulation that I did. This was when I did 20. You can see that it was very close to 0.5, but over here is when I did over 500. And the more and more simulations you do, the closer and closer your probability does get to the actual. And hopefully you had the same results. So we call a phenomenon random if an individual outcomes are uncertain, but there is nonetheless a regular distribution of outcomes in a large number of repetitions. So it's random whether or not you flip a coin and get heads or tails, but in the long run, it'll come out to a 50-50% chance. And so we call that the law of large numbers. The more and more you do a simulation, the more it's going to approach that single theoretical value. And so the probability of any outcome of chance, so again, flipping a coin is one of the most common outcomes of chance, is a number between 0 and 1 that describes the portion of times the outcome would occur in a very long series of repetitions. And remember, repetitions means doing something over and over and over again in statistics, the more simulations you do. So that is, the probability is a long-term relative frequency. So we could say the probability of some event, A, is 1. That means that it's 100% accurate. 100% of the time it's going to occur. Or you could say like the probability of event B, whatever event B is 0. That means it's never going to occur. So if you go back to going through a red light, you could say it's a probability of 0 that you'll ever approach a traffic light and it'll be blue because you only have green, yellow, or red. Or the probability of rolling feet on a dice is 0. All right, moving on. Extended warranty. So this is kind of where probability extends to the real world in the corporate world. So how much should a company charge for an extended warranty for a specific type of cell phone? So let's say that we have this cell phone and 5% of the cell phones under warranty will be returned. And the cost to replace the phone is $150. And so for the company to ensure that they're not losing this $150 on 5% of the phones, so say 5 out of 100 phones are returned, right? And they have to then fork over the $150. They need to make sure that when they charge the money for the warranty, this amount is covered so that they don't have to eat the cost. So really, you're helping to pay for, if you get an extended warranty, you're insuring yourself, but also you're helping to pay other people's phones that might break under the warranty. So if the company knew which phones would go bad, they would just charge an extra $150 for those phones and 0 for the ones that aren't going to go bad. However, the company can't know that. So they need to use the laws of probability to figure out how much they're going to have to charge people for this extended warranty so that they can cover their butts, so that they don't have to pay the extra money out. All right, this time you should be able to check your understanding. Go ahead and complete the activity. It says, according to the Book of Odds, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. So what does 0.61 mean in this setting? And why doesn't this probability say that if 100 U.S. adults are chosen at random, exactly 61 of them eat breakfast? And you might want to think of the law of large numbers when you're completing this. All right, next is probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follow to each of the statements below. Go ahead and complete that. You might want to pause the video, and I'll be right back to check your answers. So it says for question 2A, it says this outcome is impossible. It can never occur. That's an outcome of 0%, probability of 0. This outcome, it's certain. It will occur every trial. That's an outcome of 1. For letter C, it says this outcome is very unlikely, but it will occur once in a while in a long sequence of trials. And then question D says this outcome will occur more often. Question C, it would be 0.01. This means that the event occurs about in 1% of the trials. And then question D would be about 0.6%. An outcome that would occur more often than not will have a probability that is greater than 0.5. And so that leaves us with 2 choices that were not selected at all. All right, let's try another activity. And so in this activity, this is going to be investigating randomness. So you're going to perform another simulation, but this one you're going to imagine. You're not going to actually do the flipping of a coin, but you're going to pretend you're flipping a fair coin. So a fair coin means that it has a 50% heads or tails. And so you're going to imagine the first toss in your head and write down the results you see. If you see heads, write down an H, or tails, a T. And you're going to imagine the second flip. Write down those results. And you're going to keep doing this until you've recorded 50 imaginary flips. And you can record them somewhere in a space that you have on your paper. And then you're going to write your results in groups of 5 so they're easier to read, like heads, heads, tails, heads, tails. And so what we're testing in this simulation is what a run is. And so a run is a repetition of the same result. So in the example that I have here in step 3, there's a run of 2 heads. So you're going to go back and read through your 50 imagined coin flips and count the number of runs of size 2, 3, 5, 6, 7, and 8. And you can record that in the table on your paper. Then you're going to use your graphing calculator, and you're going to go to Math, PRB, select 5, which is rand int, and you're going to type in 1 comma 2 because 1's going to simulate heads and 2 is going to be tails. And then you're going to generate a similar list of 50 coin flips and record every 5 again and record the number of runs in the table. So now compare the two results, the calculator being totally random and which one has the longer run and how much longer was the run. So the idea of probability is that randomness is predictable in the long run. Unfortunately, our intuition about randomness tries to tell us that a random phenomenon should also be predictable in the short run. When they aren't, we look for some explanation other than chance variation. And so hopefully what you saw in this investigation is that in our minds and our intuition, runs seem like they're not random. But actually they're really quite common. And here's a more striking example than a coin toss. So if we look at streakiness, like when we say a shooter is hot. So suppose that a basketball player announcer suggests a certain player is streaky. As evidence, the announcer points out in a recent game where the player took 30 shots and had a streak of 7. Is this convincing evidence? Assuming this player makes 50% of his shots, how likely is a run of 7? So careful study has shown that runs of baskets made or missed are no more frequent in basketball than would be expected if each shot is independent of the player's previous shots. And so if a player makes half of her shots in the long run, his or her made shots and misses behave just like a coin toss. And that means that the number of makes and misses are more common than our intuition expects. But over the long haul, they'll come back to that, whatever their theoretical probability is. Another example, law of averages, is aren't we due for a boy? So when you decide to start a family someday, even if you have 7 girls, let's say, and you're trying an 8th time, you really want a boy in your family, you are actually equal likely to have a girl or a boy at that time. At that 8th child, it could be another girl, as equally likely as it could be a boy. So this again is just like flipping a coin or shooting a basketball. It's highly unlikely to have a run of 8 girls in a row, or to make 8 shots in a row, or to flip 8 heads in a row, but it still is likely, and it's equally likely. And so here's a nice little picture of a family of 8 girls. Whew, that'd be a lot. And so when you are performing a simulation, there are 4 steps. The first step is you need to ask yourself a question of interest about some chance process. Then you need to describe your plan. You're going to describe how to use chance to imitate one repetition of the process. And then you will record at the end of each repetition what you've done, like we did with the coin toss. Then you're going to perform many repetitions, again like the coin toss, and then conclude. Did your simulation answer the question that you had, the interest question that you had? And so when we come back, we'll look at some real life ways where you can perform a simulation. You can actually state, plan, do, and conclude on your own.